Hello everyone. We will speak about the research we did on the Tesla Model 3 for the pontoon competition. So here is Vincent Dehors, who is a security expert at Synactive, and I'm David Berard, and I work in the same team as Vincent. Pontoon is organized by ZDI. For this edition, it was announced in January of this year. It took place in Vancouver, and you can participate either in remote or on site. And for the target, there is many desktop and server softwares, and the Tesla Model 3 that we will speak about. For the Tesla, the pontoon rules are a bit complex. There is many systems that you can compromise, and there is also multiple tiers. For the tier 3, you have to compromise one system. For the tier 2, you have to compromise two systems and go deeper in the car. And for the tier 1, you have to get a full chain on the compromise 3 system from external interfaces to the final stage. The final stage can be the gateway, the autopilots, and the security module. For the tier 1 and tier 2 and 3, you have the possibility to win the car. So we will speak about the ICE ECU. It's an enclosure that contains the infotainment and the autopilots. You can find it on eBay for a reasonable price. So we did that to bootstrap our researches. On this board, there is multiple external interfaces. There is Wi-Fi connection, Bluetooth connection. There is also a connectivity card that provides LTE connection to the car. There is also an Ethernet diagnostic port that is in the car. So to access it, you have to enter the car and connect to it. And there is a connector to connect to CAN buses. And this connector also provides power to the board. So you can provide power on this port, and the infotainment computer will start normally in standalone mode. So it's quite easy to do research on this board. For the architecture of the infotainment computer, it's based on the Intel Atom SoC, which can boot on the SPI flash or in the eMMC flash. There is also a Wi-Fi and Bluetooth chipset that is external. And the second major component of this board is the gateway, which is a PowerPC SoC that also use an SD card to make his updates or to store log files. Regarding the software, the infotainment is powered by a Linux operating system. It's a highly customized build system. It can boot on the eMMC for normal boot, and for recovery boot, it uses SPI flash. The gateway is a PowerPC based on FreeRTOS. It can boot on its internal flash, on the SD card, or on the network. So there is multiple components that are connected by Ethernet. The infotainment can communicate with the gateway, the LTE connectivity card, the tuner ECU, the autopilots, and there is also the Wi-Fi chipset, which is connected by PCI Express linked direct to the infotainment system. So when you want to bootstrap research on such equipment, you need to get access to a firmware. So first we look at the internet to get such firmware, and we found someone who posts a magnet link that contains many information on the Tesla. So in this archive, there is a Tesla internal documentation, and there is also a pretty old firmware of the Model 3. So since it's an old firmware, we want to have a newer one, so we decide to dump the eMMC of the one we bought on eBay. On the same blog post as the torrent magnet link, there is also a picture with eMMC signals. So we can solder wire on this point and try to dump the eMMC from that. Our strategy to dump the eMMC is to force the ECU to boot on the SPI flash. So to do that, we just short the eMMC CMD signal. So the ECU will boot on the SPI flash in recovery mode. And we connect our single board computer with SDIO channel to access to the eMMC, and we can dump the content by using only standard Linux tools. And after that, we can disconnect our SBC, reboot the ECU, and get it work in normal mode again. So regarding the access to firmware, first we have the leaked version, then we dumped the version on the ECU we bought on eBay, and we do almost all the vulnerability research on this version. And after that, at the end of our researches, Tesla and ZDI give us access to updated firmware, so we were able to test our exploit on it. Our objective is to get a remote code execution without any user interaction on the car. And as a bonus, if we can fit the point-to-end rules to get a tier 1 entry is better. So the possible target for the entry point is the LTE connectivity card, which is a bit complex because on this card there is a Linux system that runs as a gateway, as a router between the infotainment and the modem, which is also on the card. The tuner ECU, so this one is an external ECU, so you need to have it if you want to do research on it, so we didn't look at it. Next, you have the Wi-Fi and Bluetooth chipset. This one have a very big firmware, so we spend a lot of time to look for vulnerability in it, but unfortunately, we didn't find anything. And to finish, there is the infotainment system itself. There is a pretty small attack surface on it, and we will see later. There is on the car an auto-connect Wi-Fi that is used for service. So this Wi-Fi SSID is Tesla service, and the PSK is known since it's on the leaked firmware, and it's also on the previous research. So by starting an access point, you have an additional attack surface, the full kernel Wi-Fi stack, the kernel network stack, and there is also additional surface in the network manager, which is Codeman, and we will see later more. And there is also more surface in some userland application. So I said there is already a public research on it in 2020, which is called T-Bone. And this one uses the same entry point, the network manager. So we could have named this presentation T-Bone 2. When you do vulnerability research, you want to have some debug. So we spend some time to have a VM of the infotainment system. We use QEMU with a custom kernel. We get the kernel from the kernel config from the firmware, and we had some option to make it boot in QEMU. We had some patches in the rootfs because, for example, we need to have graphic drivers that work in a QEMU. And since we want to target network attack surface, we need to have Wi-Fi in the VM. So we used Wi-Fi dongles and the USB pass-through to get Wi-Fi in the VM.
Let's talk about Codeman. There are a few alternatives to include a network manager in an embedded device. Conman is one of them. It's an open source project that run on Linux, and it's already packaged on most distribution and also on embedded distribution like the Yocto or Buildroot. In its code, we can find DHCP client, DNS client, and also a DNS proxy. There is also something called Whisper, which can do online check, for example, to detect a Wi-Fi portal. Conman can handle multiple connectivity technologies like Wi-Fi, Ethernet, Bluetooth, or even mobile technologies like using Ophono. For that, it uses a plugin system, which is quite modular. Conman has two main interfaces for local inside the system. The first one is for the kernel. It uses a netlink socket. And the second one is using a Debus server. For example, Conman can communicate with Ophono or WPA supplicant to perform network management. Also, C++ application, graphical application, which was developed by Tesla, can control Conman using Debus. And Conman is written in C and use a lot the glib, which is a sort of wrapper over the libc. We can think there is a big attack surface on inside Conman, but Tesla made a big work to reduce this surface. For example, the whole IPv6 stack is completely disabled from directly in the kernel configuration. Also, there are a lot of Conman features which are not enabled, like NTP or WPAD. So the two main locations where we can find bugs are the DHCP implementation and also the Whisper implementation, which use HTTP request. To connect to a Wi-Fi access point, Conman will first issue a scan, a Wi-Fi scan, to build a list of SSID. And if the SSID is a non-network, like a user network, like its home network, or if it is the hard-coded Tesla service network, the Conman will try to auto-connect to the access point. So it's pretty standard. It will just do a Wi-Fi authentication, and then there is a DHCP discovery and a request to get an IP address. When the IPv4 stack is configured, a Whisper connectivity check is performed, and that is a HTTP GET request. So Whisper is composed of two communications. In fact, the first one is a DNS request to resolve the name conman.vn.tesla.services. And next, Conman try to download an XML file using an HTTP GET command directly on Tesla server, which is online. We found two bugs in Whisper. The first and the most important one is an out-of-band byte swap in JWeb. JWeb is a module which contains the HTTP implementation in Conman. This bug allows to change a new line byte, which is 0A, into a null byte after the end of one allocation. This is a good bug, but quite difficult to exploit without an additional bug like an info leak. The second bug we found is a double free in Whisper. We use it in our exploit only to crash Conman. In this case, the init system will respawn Conman, and we will get a fresh start and a fresh heap to run the exploit. But after several months of exploitation, we show that in fact we could have used this bug for nasty things. So let's talk about the main bug we used, the out-of-bound byte swap. In fact, this bug is enough to get code execution alone. It is in the function receive data, which is called when there is data in the reply of the HTTP GET request. The main purpose of this function is to parse HTTP headers, and headers end with a new line. So like we can see here, the new line byte position is searched using the function memsearch. And just after, this byte is patched to be 0. And just after, the same offset is computed again, but using strlen to look for the 0. So of course, an attacker can inject some 0 bytes after before the new line byte, and in this case there is a bug. The loop will try to read the input buffer after the end of its allocation. Normally, an out-of-bound read is not really a big deal, but here we can see the primitive because the input buffer is patched with 0 bytes. So this is what we will use. To exploit such a bug, we need some more primitives, and the most important one is the ability to shape the heap. And this is exactly what gives us the HTTP parsing function, because there are HTTP headers which are parsed, and each header is splitted into a key value and are stored in a hash table. So these key and values are heap allocation, and we can create a chunk on the heap with controlled content and size. There are no limits. Also, like we can see in this example, if there is 2 times the same header, like here the header 1, the 2 value will be concatenated and stored in the hash table. This means that the first one value will be freed. And this is a good primitive because we can allocate chunk and also we can free chunk. But this spray has some disadvantages. The first one is that we cannot store null bytes and new line bytes in the chunk. And also there are a lot of unwanted allocation and free near the code. The second primitive we needed was the ability to chain 2 HTTP requests. The real difficulty is that when an HTTP request is completed, normally the spray is completely removed. But we saw a special path that allow to chain 2 HTTP requests by setting in the first HTTP request status code 100 and some fixed value in the XML file. A second HTTP request is then issued, and the spray of the first request is kept. So it's very powerful. We cannot do that 3 times, but 2 times is enough. And we use it to first, in the first HTTP request, we will shape the heap to create, to place some buffer. And in the second HTTP request, the buffer, the vulnerable buffer will be placed by the previous heap shaping. And also, we will trigger the bug in the second HTTP request. So heap shaping was really painful and boring. Mainly, the first thing we have done is to resize internal buffers to the end size, and then we fill the whole heap up to the top chunk by also with an empty T-cache. Then we create some layout and create all in this layout to place precisely what we want. The two main goals are, first, we need to control which allocation will be after the out-of-bound bug. And secondly, we want to be resilient to unexpected allocation. To exploit such a bug, it's quite complicated because the primitive is weak. But with heap shaping, we can place precisely what we want after the vulnerable buffer, and we choose the hash table values, which is an array of pointer to chunks we control. Each pointer target a chunk, and they are spaced in a way that the second byte of their address, even if we don't know them, the second byte of their address is unique. So if we have 256 pointer, we will have only one 0A byte in the second byte of the address. So when we use the bug, we can make a chunk to target the memory before in memory, and that allows us to transform a weak primitive into a good one, which is the way to have a double reference of one chunk we control. And with that primitive, we can take over any chunk in the heap that is allocated after. So when we have a takeover primitive, what can we do? In fact, we need at some point to bypass ASLR. So the idea is to choose a victim that will be given back to us at some point over the network, and to overwrite it with some data that allow to bypass ASLR. And we choose a libc pointer, a non-libc pointer, and one generic way to do that is to use the heap metadata. So we do some black magic inside the heap to place 256 times the same pointer in some location in the heap, and one of these location will be exactly at the beginning of the victim of the bug. So now we can place a libc pointer over a chunk. What chunk should we use? In fact, we have developed the info leak 4 times. The 2 first times we had a working info leak on our VM, but when we checked on the car, it didn't work because we had some bad setup. So the first time we implemented the info leak by taking over the DNS query of the WPAD module, which worked on an ECU, but after a Tesla update, which in fact replaced the WPAD function by return 0, we just it did not work. So we used our last op was the DHCP hostname. The DHCP hostname can be allocated dynamically because when conman boot, it will use the hostname of the machine. But if someone push a new hostname inside the DHCP response, it will allocate some data in memory and use it again in future DHCP queries. So to sum up, the infolic phase relies on 3 DHCP communication. The first one is to trigger a whisper query. And in the response, we push list time, which is the minimum value for list time. And we wait the DHCP renew because it should be allocated during our HTTP communication. But in fact, during Tesla update, this behavior was broken. And when we dig up, we found out that the DHCP renew in normal operation had a functional bug and don't work anymore. The fun fact is that it's a Tesla commit that introduced the bug. So as a workaround, we use the DHCP rebound. And after overwriting the new allocation with a libc pointer, we just cut the Wi-Fi access point and we wait for reconnection. Sorry. Here is a Wireshark capture showing that we got a libc pointer in the hostname DHCP request after the reconnection. With this pointer, we can compute the base address of the libc, but also in any library. So after that, that was quite easy to get code execution because we use the same method as for the leak to get one arbitrary write using the takehash poisoning method. And we use it to overwrite the content of the realloc hook of the libc. And with that, we target one gadget that allow to perform stack pivoting, and then we have a red chain. So that was the case in like February, but in fact, two weeks before the contest, we received a very, very big update from Tesla, which contained like 2 years of commits of every open source project in the system. So the libc got updated, and we lose 2 primitives. The first one was arbitrary write, because in the new libc version, we need an additional infolic to get the takehash poisoning method. And also the realloc hook we were patching doesn't exist anymore. So we can't use it. So we had to come up with another solution. And the idea is to hijack a timer. Why a timer? Because timer structure contain function pointer that are called. So we tried to look for timers, and we found one, which was the IPv6 sound router solicitation. But I said that IPv6 was completely disabled. But in the only case of the SSID Tesla service, this function is still called. It does nothing, but it is called and schedule a timer. So we use this timer. We patch the callback pointer of the structure, data structure, to target a gadget that had a leave instruction. And fortunately, RBP target our payload, so we just need this gadget to do stack pivoting, and then we have our option.
So now we have the execution pointer controlled. We also have the stack that is controlled, so we can continue our hop. But there is a limitation in size on the stack data, so we need to have a stager. So we mem protect the stack, jump on our opcodes. The stage 1 connect back to our PC, read the stage 2, and start the stage 2 in a new thread. Now we have to deal with sandboxes. Sandboxes are pretty well configured on the Tesla. There is only the things that are used by the conman process that are allowed by different sandbox. IP table filter the network for only DNS and Whisper queries. CAFL filter syscalls, and AppArmor filter access to files. There is two things that is used by conman in normal operation that are interesting. First, conman has the ability to send raw packets by using raw sockets because of its DHCP implementation. So we can use this to send packets directly on network interfaces. And in fact, this bypass IP table rules. The second one is the netlink communication with the kernel. This is used by conman to configure network interfaces, to add routes, etc. So we look at the kernel attack surface for netlink, and we found two bugs that allow LPE. Unfortunately, we start to develop the exploit like 2 days before the contest, so we weren't able to finish them before the contest. So we want to prove our exploit. So the best way to do that is have some action on the car. By default, the infotainment has the ability to send UDP messages to the gateway. The gateway will filter them and send them on the CAN buses. But conman cannot do that, but by using raw socket and sending directly the messages on the network interfaces, we can bypass the IP table and send the packet to the gateway. So we are able to send CAN messages from conman. So we have now to construct CAN messages. There is two sources of information. First, there is a partial CAN database that we can find online. And there is also a library and the file system that contain all information for CAN message decoding. So we can use data structure to rebuild a CAN database. So what we choose to do, create two CAN messages. The first one will open the front trunk and activate the whipper. The second one will open the rear trunk, switch the light on, and try to open windows. The code to do that is very simple. We just open the raw socket, bind it to the ETH0 interface, and then we build frames and send them on the socket. So here is the result. So it's in fact it was our first attempt on the real car, and you see that the trunk are open, the wiper is on, and the lights are blinking. So now these bugs are fixed. For conman, Tesla push some commit on the conman code base. So it's patched many weeks ago. And for the kernel, there is advisories that are being published few days ago. So to conclude, it was a long work. We spent almost 1 year to develop this exploit because of two reasons. The first reason is that we found the vulnerability very quickly. but since it's a vulnerability very difficult to exploit, we choose to continue the vulnerability research, and then we had to come back to the vulnerability we found because we didn't find anything better. The second reason is because we were working in parallel with Tesla updates, and we had to rewrite the exploit multiple times and for multiple parts of the exploit. At the end of our research, we had many help from ZDI and Tesla. They give us ECU that can receive updates, so we were able to test our exploit on an updated version. They also give us access to firmware, so we didn't have to dump the EMMC for each version. And they also freeze the version for the contest 2 weeks before, so we were able to test it before the event on the standalone ECU. So for all of that, thanks to them. So it was a fun research. Unfortunately, we didn't win the car, even if the impact of our vulnerability is the same of some tier 2 entry of Pontoon, but that's the rules. So thank you, everyone. If you have any question, do not hesitate to come to ask us at the social event tonight, and we will be pleased to answer them.